All right, before I work out the Laplace transform, I'm gonna just show you a list of some of the Laplace transforms. If you were to open up your differential equations textbook, it's probably inside the front cover. But we have all these different Laplace transforms here, right? And it's just a list of different things, and we're going to use it in that first step. And it looks super complicated, but once you get the hang of it, it happens really quickly. I'd like you to quickly take a look at that one right there. T squared goes to that. Okay. So continuing on with what I was saying here, so the key to what I was saying here was that we take an a sub n, like 1 over n factorial or whatever, and we use it to get to an f of x with this formula. So in this case, 1 over n factorial, e to the x. This one, cosine x. This one, ln x. And remember, it's always on an interval, but that we're not really worried about that right now. So here's what I'm going to do. I'm going to write some things. Those are called power series. We talk about them as Taylor series a lot, but power series is a more general term. So a power series, what is it? Well, it has, one thing it has is n from 0 to infinity, right? So it has n, and it goes 0, 1, 2, 3, up to infinity. The next thing is a summation. Sum from n equals 0 to infinity, right? The next thing it has is an a sub n, and that's always paired with the x to the n. And then the final, what a power series looks like, is sum from n equals 0 to infinity of a sub n times x to the n. Now, what do we get out of that? We get an f of x, right? So we get a function of x because, for example, if I take n equals 0 to infinity, then all the n's are going to turn into numbers, right? And it'll look like this, right? Or this part, ignore that. It'll look like this, right? So notice that is a function of x, right? And that's why I said we get an f of x. Now, instead of writing f of x, I'm going to call it a of x. Why do I do that? Because it goes with a sub n. Say I had a b sub n, a different sequence, and I use that, then I would call it b of x. So that's just a way to say this guy goes with that guy. Now what I'm going to do is build out the Laplace transform. So what I want you to see, you should know the difference between continuous and discrete. Something that's continuous doesn't have any holes. It just goes, right? In terms of a graph, it would be like a line. What is something that is discrete? It's like boom, boom, boom. This is discrete because it's got 0, 1, 2, 3. There is no 2.5. There are no numbers in between 0 and 1. It's just the first term, then the second term, then the third, then the fourth. So what I'm going to do is take this discrete thing, which is a power series, and turn it into something that is continuous. So instead of n from 0 to infinity, and here, let me go back up. Remember, that's the Laplace transform right there. All right, so let me, all right, so instead of n, I'm going to use a different variable. We're going to take t, and it's going to go 0 less than or equal to t less than infinity. Or I could say 0, whoops, thinking and talking at the same time, 0 up to infinity. Those are my t values. Next, what's the equivalent of summation, but a continuous version of summation? Well, you've been through calculus. You know that would be the integral from 0 to infinity. And it would be a dt, right? And then instead of an a sub n, what I'm going to do is take an f of t. And you'll see how this puts all together in a moment. And what do I get? I want to write this thing out. So sum a sub n goes to sum a of x. So what I get is, instead of a summation, I get the integral from 0 to infinity. Instead of a sub n, I'm going to put f of t. I'm going to write x to the n, right? Write x, and then, is it an n? No, remember, the n here got replaced with a t. So I'm going to write x to the t. And we're integrating with respect to t, so I wrote a dt. Why is that? Because the 0 and the infinity, they're t values. Now, what I want you to see, let's go back up here to all these examples, these top three. I was integrating with respect to x. My answer didn't have x's in it. Integrating with respect to x didn't have x's. Integrating with respect to x but had an a in it. My answer is numbers with an a. So come down here. That's why I wanted you to do that. If I integrate this with respect to t, all the t's are going to go away because it's a definite integral. But look, x would be left, x would still be there. So I get a function of x, right? I would get a function of x out of this just like I get a function of x out of this thing, and I use a capital F because it is associated with the lowercase f. Hopefully you see that this structure is the same as this structure over here. Now I'm going to do some work to make it look better because there is a big problem with that. I just copied this and I wrote f of x is this. And it's not practical because it's hard to integrate. I'm going to show you why. Take f of t equal to t squared. Or take f of t equal to sine t. Or take f of t equal to 1 over t. If I wanted to evaluate this thing, then I would get a bunch of integrals for each of these. That would, f of t would get replaced by each of these. So if I wanted to find the Laplace transform for t squared, right? What I would, or in this, if I wanted to plug in f of t for this thing right here, I would do the integral from 0 to infinity of t squared x to the t dt, or the integral from 0 to infinity of sine t times x to the t, or the integral from 0 to infinity of dt of 1 over t x to the t dt. Now, it may just like look weird and you may not see why this is difficult to integrate. So remember, just like I did with the a up way up here, I just treated that as a constant, right? So if I try to treat x as a constant, which is legitimate here, right? When I do this integral, I run into a problem. Let me show you why. Say x was equal to, let's go with 8, okay? So for this first one, I would get the integral from 0 to infinity of t squared times 8 to the t dt. Now, you may know how to integrate this, but it is not something that jumps out to your head. It also gives us really, really terrible numbers. So this is not something that we want to integrate. Imagine if that was 8 to the t and I was trying to integrate with respect to t. It would get bad really fast, right? This would get bad. But there is a base that we know how to integrate. The integral of something to the t dt. What do I know how to integrate? I know how to integrate the integral. I know how to do the integral of e to the t. So if my base was instead of x and e, then maybe, just maybe, I can integrate that. So what I'm going to do is convert this thing right over here to an exponential, and it'll become much, much easier to integrate. My goal here, I just copied and pasted that line again, is to replace x to the t, highlighted in yellow, with e to the something such that that e to the something is integratable. Because it'll make it so that I can calculate this integral using ideas from Calc 1 and Calc 2. So, where do we start? Well, I know that x is equal to e to the ln of x. That's because e to the n ln are inverses. You should be familiar with that. Well, I can raise it to the t power. That means x to the t is equal to e to the ln of x to the t. So what I'm going to do is change that ln of x. I'm going to change this little piece right here. Okay? You may be like, say what? Well, let me just walk through it. I need to start with when this thing will converge. What I mean by converge, this thing, imagine if I had x equal to 8, for example, right? If I had 8, I would get 8 to the t. T is running from 0 to infinity. This thing would diverge because that 8 to the t would get bigger and bigger and bigger as I got out to infinity. I'm trying to argue to you that x needs to be between 0 and 1. Otherwise, this thing will explode if it's bigger than 1. And if it's less than 1, then I'm going to get complex and imaginary numbers in here. So, first off, 0 needs to be less than or equal to x and less than 1. And then what I can do is I want to know what, basically I want to look at what this thing is right here, right? So since I've got in blue right there an ln, let me take the ln of both sides, and I'm sort of breaking math a little bit, but it's okay, less than ln of 1. The reason I'm breaking math is because ln of 0 doesn't exist, right? If you know what the graph of ln looks like that. This shoots down. It goes down asymptotically. It crosses at 1, right? So if this was an x-axis, this would be x from 0 to 1, and this graph would be ln of x. So if my input for ln, x, is limited between 0 and 1 because I want this integral to converge, then the question is, what's ln going to be between? Well, I know ln of 1 is 0, and I know that ln of 0 goes to negative infinity. So I can, if this is true, then that is true. I could rewrite that. All right, so ln is between negative infinity and 0. I could rewrite that as ln of x is less than 0. Those statements mean the same thing, right? If something's between negative infinity and 0, then it's less than 0. And then what I can do is write that negative ln, well, if ln is negative, then negative ln of x is going to be positive. So it's going to be greater than 0. Now, what I'm going to do is replace that ln of x with a new variable. I'm going to say back it up there a moment, sorry. I'm going to let s equal negative ln of x. That's this thing, and that means that negative s is equal to ln of x. Why do I do that? Remember, this ln was going to get replaced with something, right? To make it so that this thing is then integratable with this t here, right? So if I let s be negative ln of x, then, let me zoom out a little bit here. In that blue up there, I'm going to take ln of x and replace it with s right there. So I get x to the t is equal to e to the ln is negative s raised to the t. Well, that, by exponent rules, tells me that x to the t is, just equal to e to the negative st. Now you may say, what? Okay, look, the whole point here was to replace this x to the t with something that is integratable. So if I sub this in right here, what I get is the integral from 0 to infinity of f of t times e to the negative st dt. And that was just by doing this, quote, simple, quick changeover. And look, let me go up to the very top of this thing. Integral 0 to infinity of f of t times e to the negative st dt. So what I want you to see, well, I mean, it's like really long. And I have to make a point, but look, it was power series. Let's make it continuous. Let's mess with it and make it usable. And we get this. One thing I need to say. All right. If ln of x, if ln of x is less than 0 and negative ln of x is greater than 0, look here. Negative ln of x is the same as s. So since negative ln of x is greater than 0, then s has to be greater than 0. So this is true for s greater than 0. And it should be equal to, I think. Well, anyway, s greater than 0. Boom. There's your Laplace transform, and we'll do an example in a moment.